Partial replacement of cement with rice husk. Ash in cement concrete. Abstract concrete is one of the significant materials of the construction industry. These days, because of expansion in a population, the demand of infrastructure is expanding day by day. This prompts the increment in production of cement. In the present scenario, the overall cement production is about 4.1 billion metric tons worldwide. This huge amount of production prompts utilization of natural resources, and it is for unsafe for environment. Enormous amount of waste byproducts are delivered from the manufacturingenterprises, for example, mineral slag, fly ash, silica fumes, rice husk ash and so on. The rice husk ash is an agricultural byproduct which is obtained from the rice mills. The husk which is obtained from mill is of no use, i.e. it is not even be used for animals to eat. Hence it is used as a fuel in various big industries. The burning temperature is very high, hence they are obtained from that. The RHA is very lightweight. The research work here deals with the partial replacement of cement with RHA in concrete at various percentage such as 0%, 5%, 10%, 15%, 20%, and 25% by mass of cement. Various experimental investigations are carried out to find out the compressive strength, split tensile strength and of concrete samples cured for period of 7 and 28 days. The results obtained from the experiments with satisfactory replacement of cement with rice husk ash are presented in this research paper. Keywords: concrete, rice husk ash, compressive strength, split tensile strength, flex URL. 1. Introduction. Concrete is a most broadly utilized construction material. It is, all in all, a mixture of cement, binding material, aggregate, filler materials, admixture, and water. It very well may be formed in any necessary shape, simple to deal with, and has a wide range of design strength. It is therefore utilized in approximately all benevolent construction work. Cement is the main element of concrete as to act as a binding material. Be that as it may, the production of concrete causes so numerous natural risks, like cement dust, air contamination, solid waste pollution, noise pollution, ground vibrations, and resource depletion because of crude material extraction. The primary components of the gases produced from cement enterprises are CO2, N2, O2, SO2, water vapors, and micro-components, for example CO and NOx. The cement industry is one of the two biggest producers of carbon dioxide, CO2, making up to 8% of overall man-made emanation of this gas, of which half is from chemical process and 40% from consuming fuel. The CO2 produced from structural concrete is assessed at 410 kg per cubic meter. Around 900 kg of CO2 are discharged for the creation of every 1 ton of concrete. The CO2 is major greenhouse gas. In this way, cement assembling contributes greenhouse gases both straightforwardly through the decay of calcium carbonate and furthermore through utilization of energy, especially from the combustion of fossil fuel. Thus we are expected to discover other discretionary material for concrete instead of cement. In the event that we ready to supplant few percent of cement from concrete, it will supportive to lessen CO2 emission. From different exploration works, some mechanical squanders are discovered which can diminish the measure of concrete in cement without bargaining its essential properties, like strength. Granulated blast furnace slag, silica fume, rice husk ash, cenospheres, and fly ash are some industrial waste that can be utilized as strengthening cementitious materials. Rich husk ash is an agricultural byproduct which is obtained from raceme lanthan burned and very high temperature as fuel. Which gives some extra advantages when utilized in cement. Before additional conversation about RHA, let us quickly examine about concrete. 2. Objective of research. To examine the gainful use of modern waste as the cement substitution in construction work. To evaluate the optimum proportion of rice husk ash as a beneficial replacement with cement in cement concrete. 3. Material used. 3.1 Cement. For this research work, PCC cement of Ultratech Cement Company is used, that is available in our nearest construction material shop. While adding cement in concrete mix, it is ensured that cement is moisture-free and no lumps are found in the cement bag. 3.2 Rice husk ash, RHA. RHA is the result of burning of rice husk. A large portion of the evaporable parts of rice husk are gradually lost during consuming, and the essential deposits are the silicates. The attributes of the debris are subject to 1. Arrangement of the rice husks, 2. Consuming temperature, and 3. Consuming time. Each 100 kg of husks consumed in a heater, for instance, will yield around 25 kg of RHA. For this experimental work, the rice husk ash is purchased from a reliable source, Ambika Traders, situated Anand, Gujarat. 3.3 Fine Aggregates. Fine aggregates are the material going through an ISC 4.75 mm and hold onto 150 m gauge. Locally accessible sand ice utilized as fine aggregates in this experimental investigation. 3.4 Course Aggregate. The aggregates which may infiltrate 75 mm IS strainer and held on 4.75 mm IS sieve is called coarse aggregate. Size of coarse aggregate may change from 10 mm to 40 mm. Locally accessible coarse aggregate is utilized for test, that accessible on closer construction material shop. 3.5 Water. Generally water having pH value 6.0 to 8.0 is used. It is potable water i.e. not containing any type of alkalinity and salinity. 4 Methodology. 4.1 Proportioning. The standard proportion according to IS 456-2000, for M20 grade concrete is 1:1.5:3. Here extent is embraced 1:1.80 11:3.283, which is determined by mixed design method. Concrete is supplanted with RHA at different rates, for example 0%, 5%, 10%, 15%, 20%, and 25%. The measure of every fixing utilized per cubic meter is as follow: concrete equals 363.498 kilograms, fine total equals 683.812 kilograms, coarse total equals 1329.614 kilograms. 4.2 Casting of samples. Total 108 samples are cast out, 36 cubes, 36 cylinders and 36 beams are prepared. Concrete mix is filled in molds in 3 layers. Each layer is compacted by tampering rod with 25 number of blow. 4.3 Curing. The sample specimens are set apart inside 2 to 3 hours of casting and are kept in vibration-free place, in almost 90% relative damp air and at temperature of 270 plus or minus 20 C for 24 plus or minus 1/2 hours. After this period, the specimens are put in submerged condition in fresh water in a tank and are kept there only before to test. The duration of curing of sample is according to their schedule of testing. 4.4 Testing of samples. Compressive strength test. The IS code followed for testing IS 516 to 1959. The concrete cubes are cast of size 150 mm times 150 mm times 150 mm. These samples are tested in UTM, Universal Testing Machine, of capacity 2000 knots at pace of 140 kg/cm2/min. The compressive strength test is performed at 7 days and 28 days. Split tensile test. This test is an indirect method for finding tensile strength of concrete. The cylinder of dia 150 mm and height 300 mm is cast and afterward tested at 7 days and 28 days. The loading rate is kept 1.2 MPa. Flexural strength. The beams of size 100 mm times 100 mm times 500 mm were cast for this test and 1-point loading method is adopted for testing. Tests are performed per the ASTM C293. The tests are performed at 7 and 28 days. 5 Results and discussion. The compression test results are shown in Table 1. From Graph 1 it is observed that the maximum result is obtained at 15% rice husk ash in concrete. The 28 days compressive strength for conventional concrete is found 27.75 MPa and that for 15% rice husk ash concrete is 32.78 MPa. It shows the 15.34% improvement from conventional concrete. Thus optimum use of rice husk ash is 15%. Graph 2, Split Tensile Strength Analysis. The split tensile strength test results were shown in Table number 2. From Graph 2 it is observed that the maximum result is obtained at 15% rice husk ash in concrete. The 28 days strength for conventional concrete is found out to be 1.697 MPa and that for 15% rice husk ash in concrete is 1.380 MPa. It shows the 24.41% improvement from conventional concrete. For other percentage of rice husk ash the strength is getting low, thus optimum percentage for use of RHA is 15%. 6. Conclusion. The compressive strength of conventional concrete at 28 days is 27.75 MPa and 15% rice husk ash concrete is 32.78 MPa, it show the 15.34% improvement from conventional concrete. For other percentages of RHA, rice husk ash, the strength is below 20 MPa, thus optimum percentage of RHA is 15%. The split tensile strength of conventional concrete for 28 days is found to be 1.526 MPa and that for 15% rice husk ash concrete is 1.697 MPa. It shows the 24.41% improvement from conventional concrete. The optimum use of rice husk ash is 15%. Finally, from the experimental analysis we have found that 15% replacement of rice husk ash with cement in cement concrete is beneficial replacement. And we go beyond this for further replacement in percentage of cement we will see decrease in strength of concrete. 7. Acknowledgement. I would extremely like to thanks to my mentor Professor M.C. Palival, for his constant support and motivation during the course of my thesis work. I truly appreciate and value his esteemed guidance and encouragement from initiation to the completion of the thesis. His valuable guidance will be remembered lifelong. Special thanks to God for everything and family members for always encouraging me to push the limits.